All right, so we went over a couple properties of the gamma function already, right? We went over the recursive property, which is this thing, and in the previous video, we went over this right here, the Euler reflection formula. Now, there is one more important property of the gamma function that we use quite often, known as the Legendre duplication formula, or however you pronounce his name. But to figure that one out, I think it's easier to do it after we introduce a new function. Now, this function is a multivariate function known as the beta function. So it's going to have two inputs, x and y, and its definition is also with an integral, kind of like the gamma function. It's the integral from 0 to 1 of, and the inside is going to be t to the x minus 1 times 1 minus t to the y minus 1 dt. So that's the beta function, but why are we introducing this, and how is it connected to the gamma function? Now, interestingly, before we get to that, the beta function is known as the Euler integral of the first kind, while the gamma function is known as the Euler integral of the second kind. So you can kind of see that they're already sort of related, just by their name and how they're categorized. But now, today we're going to, derive an identity, a very important one and a common one that we use a lot, that connects these two functions, okay? So the beta function, in terms of the gamma function, is gamma of x times gamma of y divided by gamma of x plus y. Now, this is very nice and symmetrical, and using this, you can in fact see that y and x are commutative. Basically, you can swap where y and x are, and the answer will be the same, even though it might not immediately seem like that inside of the integral. Okay, but now I want to figure out how this identity right here comes to be. Now, let's manipulate it to make it a little bit simpler. Okay, multiplying gamma of x plus y on both sides. So yeah, gamma of x plus y on both sides. You get on the left-hand side gamma of x plus y, and you have the beta of x comma y. On the right-hand side, very simply, you have gamma of x times gamma of y. Now, we're going to need some multivariable calculus for this, because the way we're going to deal with this is just straight up deal with the integrals. Okay, on the left-hand side, let's use s and t. So, up here, gamma function is just integral from 0 to infinity. We're going to do t to the power of, well, it's your argument. Here, our argument is x plus y. So t to the x plus y minus 1, and then e to the negative t dt. And here, our beta function, we're just going to copy this down. It's literally beta of xy, so we're not going to do this in red. Let's do this in black. Integral from 0 to 1. Let's use s to the x minus 1, 1 minus s to the y minus 1 ds. All right, and so let's work starting from here. First thing you notice is that the two integrals are completely independent of each other. Okay, that means there is nothing in terms of s inside of this integral, and nothing in terms of t inside of the s integral. So that means we can draw the two together. They're constants in terms of each other, okay? So let's bring the s integral inside the t integral, and that's going to look like, and I'm going to put an equal sign there. Integral from 0 to infinity, that's the t integral. Then the integral from 0 to 1, that's the s integral. And then let's just write stuff down, okay? Inside, let's put down this t to the x plus y minus 1. And let's put down the s to the x minus 1, 1 minus s to the y minus 1. And then we have this e to the negative t. All right, and now we get to close the integral. This inner integral, once again, is in terms of s. The outer integral is in terms of t. So ds dt. Okay, so it looks sort of complicated now. Let's see if we can consolidate this a little bit. Actually, you know what? In order to find how you deal with this, because right now it just looks like you can't really simplify any of it, let's get a sense of direction, like where to aim, by observing the right-hand side now, all right? So the right-hand side, let's just write it out as well. So right-hand side, let's write it out in terms of integrals once again. Gamma of x is just, what variables do I use? I'm going to use u and v, okay? It's just u to the x minus 1 e to the negative u du times, all right, so that's gamma of x. And then now for gamma of y, we have integral from 0 to infinity, w to the y minus 1 e to the negative w dw. Okay, so this is just the right-hand side. And let's interlace them and see what kind of targeted form we're trying to get, okay? So once again, you know, these two integrals are completely independent of each other, right? They're constants in terms of each other. So kind of like what we did here, we can bring it together, interlace the integrals. So we're going to have the integral, double integral going from 0 to infinity on both. Let's copy this u to the x minus 1 down. And then this w to the y minus 1. And then let's copy down the exponential. So e to the negative u times e to the negative w. They both have a base of e, so you can combine the powers and then factor out the negative sign. So after factoring out the negative sign, that's going to go on the outside. Inside, you have u plus w. All right, and then you close it with du dw, I guess. Or dw du. It doesn't really matter. Okay. So we were told that these are equivalent, right? And we're trying to prove that now. We know, and we just figured out that the left-hand side of this is equal to this weird-looking thing, and the right-hand side looks more like this. So how do we get them to look more like each other? Well, let's make a few observations. Here you have an exponential term, and that kind of matches with this exponential term. And then right here, you have something to the x minus 1 that matches with this u to the x minus 1. You have something to the y minus 1 that matches with this w to the y minus 1. You have this extraneous guy hanging out here. Let's try to take this guy and work it into this x minus 1 and this 1 minus s. Okay. Up here in this power, the way we can try to work this factor into these other two is by making the powers the same. So what we can do is we can do x plus y minus 1. We can rewrite as x minus 1 plus y minus 1. Okay, but remember earlier we only had 1 minus 1, so now we have to add 1 back, if you can see that. So now we have this x minus 1 and a y minus 1. All right, so rewriting this, you get t to the x minus 1, okay, and then times t to the y minus 1, and then you have this lonely plus 1. So we're going to drag that out here, okay? We're going to insert it right here because, you know, it's not really part of the structure. Okay, so now that you have this is just that, let's go ahead and combine this t to the x minus 1 and this s to the x minus 1. And what we're going to get is, well, let's write down the double integral first, from 0 to infinity, then from 0 to 1. This t to the x minus 1 and s to the x minus 1 are going to combine. We're going to get ts all to the x minus 1. And then similarly, right here, we're going to combine this t to the y minus 1 with this 1 minus s to the y minus 1. So we're going to get t times 1 minus s to the y minus 1. And then we have this e to the negative t behind here. And then this lonely t sitting out with the differential elements. So, we kind of have like a structure going on now. We see that this ts is analogous to this u, right? Because they both have a power of x minus 1. This t times 1 minus s is analogous to this w because they both have a power of y minus 1. And this t is analogous to u plus w because they're both exponentials. This t you can leave alone for now. Let's just make the assumption that it's part of the differential element. Now we're going to do a change of variables from ts to wu and see if we get that integral. So I just copied everything down a little bit higher so we have more room to do our work, okay? But you see the same exact thing. You know, here you have the connection between beta and gamma. Here's the manipulated form. This is the double integral that was on the right-hand side, and this is the double integral we were just working with, okay? Now, we want to do a change of variables from the S and T world to the U and W world, okay? Oh, by the way, these two differential elements you can reverse because, you know, the bounds are the exact same. So if we want in terms of du dw, then, I mean, we could just do that, and that's by Fubini's theorem, okay? All right. So this, in order to move over to the U and W world, we have to calculate this. This is known as the Jacobian, all right? But we also have to calculate the bounds. We'll do that in a second. So we have to find S in terms of U, and S in terms of W and U, so that way we can actually take its partial derivative. And we also have to find T in terms of W and U. Now, we kind of have that given to us already, okay? We're going to set this up so that the exponents match. So right here, we're going to set T to be equal to U plus W. So right here, T is going to be equal to U plus W. All right. How about S? Okay, well, we need to find that now. Notice that TS here is, earlier, like I mentioned, is analogous to U. So if we have TS equal to U, how do we isolate S in terms of U and W? Well, if you go ahead and take this right here and divide it by that, on the left-hand side you get TS divided by T, which is going to give you S, so that's nice. On the right-hand side you're going to get U divided by U plus W. So now we have S in terms of U and W. All right, let's go ahead and calculate this Jacobian now, all right? Let's calculate the four partial derivatives. All right, partial derivative number one is partial S, partial U. So if we're gonna take the derivative of this with respect to U, it's just quotient rule, yeah? So quotient rule meaning you take the bottom, let me see if I remember quotient rule. Take the bottom, copy it up to the top, so you're going to get U plus W, and then take the derivative of the top, so that's just going to be 1. Subtract off, keep the top, so that's going to be U, and then take the derivative of the bottom. When you take the derivative of the bottom, W is going to go to 0, because remember, this is a partial derivative with respect to U, so W is a constant, and then U is just going to go to 1. So in actuality, up here, it's just going to be a minus U. So at the end of the day, the numerator, the U and U are going to cancel. You're going to simplify that down to a W. And then the denominator in quotient rule is just the original denominator but squared. So we're going to have U plus W squared. All right, that's nice. Let's calculate the next partial derivative, partial S, partial W. It's the same, actually it's almost the same thing. We're not going to use quotient rule for this because notice that you can rewrite this as U times U plus W to the negative 1. And now that U is a constant because we're doing this with respect to W, U is going to stay. And then when we take the derivative of this part right here, well, the negative 1 is going to drop down to the side, so we're going to get a negative sign. And we're going to subtract 1 from the power, so it's now going to be U plus W to the negative 2. And we can just write that as the U plus W squared in the denominator. And then chain rule, we have to take the derivative of the inside with respect to W, but that's just 1 because U is going to go to 0 and W is going to go to 1. So there we go. That's our partial derivative with respect to W. Now let's go work on T, and T is much easier. So here, when you take the partial derivative with respect to U, partial T, partial U, this W is going to go to 0, this U is going to go to 1. And then same thing when you take the partial derivative with respect to W. This U is now going to go to 0, and this W is now going to go to 1. So partial T, partial W is also going to be equal to 1, and that is very nice. So now we can go ahead and plug it in. I'm not going to erase this, actually. Let's copy it down here. T equals U plus W, S equals U over U plus W. All right. let's plug it into here. So this is still going to be the absolute value of the determinant of this right here. In fact, we can calculate the determinant straight up. So let's take the absolute value. Okay, the determinant is partial s partial u times partial t partial w. So we're going to take this guy right here and multiply it with, this guy right here. Okay, I'm going to put a dot. When you multiply this times 1, it's just going to be that. So we're going to be left with w over u plus w squared. Subtract off this other diagonal. So that's just the other two partial derivatives. That's going to be negative u over u plus w squared. And these two negatives are going to cancel out and make a positive. Now, you can see here that this is just w plus u over u plus w squared. The top is going to cancel out with the square. You're going to be left with the absolute value of u, just 1 over u plus w. All right, and u and w are, well, we're going to have to calculate the bounds later, but you can see that they're going to work out to be greater than 0 either way. So the absolute value of this is just going to be itself, because it's always going to be positive. Yeah. So we just found that ds dt is just this guy times du dw. In other words, notice that this right here is just 1 over t. Okay, so we can also write it like this. So ds dt, we saw that this Jacobian guy worked out to this. The bottom is just a t, so this can also just be rewritten as 1 over t du dw. And if you multiply t on both sides, it works out perfectly. You're going to get a t ds dt, and that's going to be equal to just du dw. And why is that nice? Well, because this exactly matches up with that, right? And this matches exactly with that. So there we go. Now we are almost done, but there's a couple other things we have to work out, and that includes the bounds. So let's work from here, okay, and we'll see if it ends up being equal to this. That is the game plan. All right. So we're going to have a double integral, and we'll sort out the bounds in a second. All right. Ts is t times s. When you multiply these guys together, the u plus w is going to cancel with the u plus w. You're going to be left with the u, so that's nice. And it's going to be to the power of x minus 1. T times 1 minus s, well, that's a little bit more difficult, but it's not that bad. Take u plus w, which is t, okay. 1 minus s is just 1 minus u over u plus w. But you can simplify that because 1 is just u plus w over u plus w. Now notice that this u and that u are going to cancel. So you're going to be left with w divided by u plus w. Okay, and very simply, this guy is going to cancel with that. So you just found that t times 1 minus s is just w. And that is very elegant. So w to the power of y minus 1. And now you just have e to the power of negative t. T is u plus w. So yeah, we have that matching as well. I mean, like earlier we set t to be u plus w, so of course it has to match. Now let's, and also, wait, one more thing. T ds dt is just du dw. All right, so the differential elements match. The entire integrand, notice they're the exact same as we intended to happen. What about the bounds? Are the bounds going to work out at all? Well, let's figure that out. So we don't need these partial derivatives anymore. Let's see. Now, to calculate the bounds, we actually need u and w in terms of t and s. So, I mean, they're already isolated, right? We did that work for us earlier. T times s is just u. So, u equals t times s, okay? And then t times 1 minus s is just w. So w is just t times 1 minus s. Okay. How are we going to do this? Well, notice that t goes from 0 to infinity. Okay. So t is going to be able to go from 0 to infinity. And depending on this other factor right here, w might also be able to go from 0 to infinity. And same deal here. Okay. Now, the other factor, when it comes to u, s is between 0 and 1. So the lowest it can possibly get is going to be 0, right? That's going to be in the case where one of these guys is 0. The highest it can possibly get is just infinity, because that's the case where s is above 0 and t is at infinity. So u is going to be able to go from 0 to infinity. All right. How about w? Because this is a little bit weird, but it's really not, because once again, t can go between 0 and infinity. 1 minus s, on the other hand, well, s is between 0 and 1. So the biggest this factor can get is when s is 0. That's when this factor is equal to 1. Okay, the smallest this factor can get is when s is equal to 1. 1 minus 1 is 0. So this factor ranges between the values 0 and 1. So it's exactly like this case up here. Infinity, right, and something that goes between 0 and infinity multiplied by something that goes between 0 and 1, well, that gives you the whole range of numbers, once again, between 0 and infinity. So w is an element of 0 to infinity. So this inner bound is in terms of u, so we're going to have the inner bound be 0 to infinity as we calculated. Sorry, not the inner bound, the inner integral. And the outer integral is also 0 to infinity, because w goes from 0 to infinity. So there we go. We are now done, because we have proven that this integral right here, which is the left-hand side of this, after you make a change of variables, is precisely equal to this, which is that. And that we found is the right-hand side. So we just proved that the two sides are equal after you rewrite them in terms of an integral and then do a change of variables. So there you go. That's how we proved that this property is true. And we're going to be using this in the next video about the Legendre duplication formula, or however you pronounce it.